Hello, my name is Jeff Messier. I'm a professor in electrical and computer engineering in the Schulich School of Engineering, and this is Module 16 in my Computer Networks lecture series, where we talk about routing a packet across a multi-hop mesh network. And so this is, we're starting kind of a new large topic in the lecture series. And so whenever we do this, I like to sort of step back and take a look at our sort of big picture protocol stack and just take a look at where we are. And so just to kind of summarize or recap what we've talked about so far, at the very start of the lecture series, I talked about the physical layer. And the purpose of the physical layer is to basically just translate ones and zeros into analog waveforms that can travel over an analog channel, maybe a wire or a wireless channel, be received by the physical layer in another device, and translated back to ones and zeros. And we didn't talk about that too much in this lecture series because this falls into the digital communications area of electrical engineering, and there's whole courses dedicated to that topic. The next layer up, which we spent a lot of time on, was the data link layer, layer 2. And the reason why we spend a lot of time on it is because there's a lot of functionality packed into the data link layer. We have two sub-layers. We have the logical link control layer, and the logical link control layer basically exists to make an error-prone physical layer appear to be error-free. And we do that by retransmitting bad frames using the ARQ mechanism. The ARQ mechanism, of course, is used in other layers of the protocol stack, so we're going to see it again, but we introduced a lot of the ARQ theory during our discussion of the LLC. The next big topic we talked about was the medium access control layer, or MAC layer. And the MAC layer is meant to kind of coordinate access to a shared channel. So we've got a bunch of nodes together competing for a common channel, and we need to kind of control how these nodes communicate over the shared channel because they can potentially interrupt and interfere with each other. Now, arguably, well, not even arguably, I mean, certainly whenever you have more than two nodes communicating, you can say that you have a network. And so the MAC layer discussion was really sort of the first point in our lecture series where I think we were truly dealing with networking. However, it was a special kind of network where every node can transmit directly to every other node. What we're going to talk about now is layer 3 of the protocol stack, which is known as the routing layer or the network layer of the protocol stack. And the purpose of layer 3 is to tackle the problem where we have a network of nodes where each node can't necessarily transmit directly to the node that it's trying to reach. And this brings us really into the topic that will bring us into understanding the internet. And so this is really kind of my favorite section of the course because once we finish talking about the network layer, about layer 3, you'll really understand basically how packets travel across the globe over the internet from one computer to the other, which is really a very powerful bit of information. So we've already talked about how the internet, or a packet data network, is often represented using a mesh topology. And I've shown an example of one possible mesh topology on this slide. In this topology, we have a source node, S, that wants to send a packet of information to a destination node, D. And the source and destination node, unlike during our MAC discussion, the source and destination node cannot transmit directly to each other. And they communicate instead through a series of intermediate nodes, which we call router nodes. And that's what I've indicated, or they're represented by these R nodes. And typically in a mesh network, there are multiple paths that a packet of information can take through the network. So the source node will send a packet to this first router, but then the router has several choices of where it can send the packet next. It could send the packet along this path, in which case it can be transmitted directly to the destination. However, we could also choose some intermediate paths as well, some shorter, some longer. And the job of the network layer, or layer 3, is to, first of all, find the best route through a mesh network for a particular packet, and also ensure that the routers know how to forward each packet along that route. So there's kind of two problems. One is to determine the path through the mesh network, and the second problem is to make sure that the routers know what to do in order to forward the packet along that path. And in this discussion, we're going to be focusing primarily on the Internet Protocol, or IP, which is, really the most important layer 3 example. So why is designing layer 3 such a big deal? Well, designing the network layer for the internet is a particularly huge technical challenge because of the particularly huge scale of the internet. So to just throw around some statistics, there are currently internet users in 214 countries around the world. And so that means we're designing a routing protocol for a network that is truly global in scope. Your computer at home should be able to communicate with any other computer literally around the world. So we've got a massive geographical scale for the network. We also have a huge number of just raw devices plugged into the internet. So in 2019, over half of the world's population used the internet, and the number of internet connected devices in 2020 is expected to exceed 31 billion. Every single one of these devices needs to be able to communicate with practically every single other one of these devices. And so a lot of what we're going to be talking about when designing layer 3 is specifically geared towards dealing with the scale, the massive scale of the internet. And there's basically going to be two main problems that we're going to discuss. Number one, how do we address all of these devices? And obviously, we have numbers big enough for 31 billion, so we could just make really long integers and give everybody a different unique integer address. But it's going to be a little more nuanced than that, because addressing, as it turns out, is going to be very related to how we practically enable routers to deal with all of these possible destinations. And that leads us to the second challenge or problem. How will the routers know how to handle packets with so many potential destinations? So really, your little router box at home in your house has to be able to deal with packets that could be destined for, over 30 billion possible destinations. So how are we going to possibly handle this? And so that's really going to guide our discussion of the network layer. And our discussion of the network layer, again, is very specifically going to focus on the Internet Protocol, or IP, because that's really sort of the rock star protocol of layer 3 for sure. And so to kickstart our discussion of the routing layer, what I want to do now is introduce the concept of a routing table. And also just, exactly what are these router nodes that we're sort of talking about, these intermediate nodes. A router is basically just a special purpose computer with several network interfaces. And so if we have, for example, in our previous picture, if I have one of these R nodes with, maybe 3 connections, this would basically be a computer with 3 network interfaces, right? So 3 Ethernet cards, and each of these lines would correspond to a different Ethernet connection. And that's kind of what I've shown a little bit in more detail in this slide. So in this case, we have 4 computers, 4 personal computers. Each computer has 1 or more Ethernet cards, and I've used the ETH0, ETH1 convention for referring to Ethernet interfaces, which is kind of the Linux convention, or one of them anyways. Each one of these Ethernet cards is connected to an Ethernet switch, and so we have 3 Ethernet switches. And personal computer 1, PC1, wants to send a packet to personal computer 4. And PC1 is not directly connected to PC4 like we had with the MAC algorithm discussion. And so we have to send the packet, in this case, through 2 intermediate nodes, PC2 and PC3. So PC2 and PC3 are essentially the router nodes for the purposes of this example. Now, a router does not need to store the entire path that a particular packet is going to traverse when it goes across multiple hops on a mesh network. All each router really needs to store is the next hop for that packet, or the next path that packet needs to take. So PC2 doesn't need to know what happens to the entire, or it doesn't need to know the entire path of the packet. It just needs to know which of its Ethernet interfaces to send the packet on, or to forward it on. And it stores that information in what's known as a routing table. And so each one of the computers in our mesh network is going to have a routing table. And the routing table basically has, if you can imagine, sort of 2 columns. The first column is going to store addresses. And then the second column is going to store the network interface that we use to send a packet to that particular address. And so the routing table in PC1, and so the way the routing algorithm will work is the computer will take the packet, take a look at the destination address, use that destination address to look up an entry in the routing table, and that routing table will tell the computer which network interface to use to send that packet. And so we start with PC1. So PC1, even though it's the source computer, will still have its own routing table. It creates the packet, it addresses it to PC number 4, then it looks up the address for PC number 4 in its routing table, and the routing table says, send the packet out on Ethernet 0. Now, if you look in this picture, PC number 1 only has 1 Ethernet interface. And so as you can imagine, basically all packets it sends are going to use Ethernet 0. And we'll talk about default network routes later on when we get into our discussion. But for now anyways, the routing table for PC1 tells us to send the packet out Ethernet interface 0. It goes over the switch, comes in on Ethernet interface 1 for PC number 2. Now PC number 2 is going to take that packet, it's going to look at the address field, and it's going to first check to see if the packet is for it, and if it is, it keeps it. But if it isn't, it needs to forward it along its multi-hop path. And so it's going to take a look at the address and it's going to say, oh, this is for PC number 4. Then PC number 2 will look up the PC number 4 address in its routing table, and the routing table will say, send this packet out on Ethernet interface 2. And that is what PC2 does. Now you'll note that PC2 doesn't, the routing table doesn't then say, oh, just for your information, there's two more hops. PC number 2 only ever knows it, only ever stores next hop information. And anyways, the packet arrives on Ethernet interface 0 at PC number 3. PC number 3 is going to take the packet, look at it, see that it's not addressed to PC number 3, so it needs to be forwarded on. And so PC number 3 will look up the address for PC number 4 in its routing table, see that it is supposed to send that packet out over Ethernet interface 1. That's what it does. It arrives at PC number 4. PC number 4 is going to receive the packet, look at its address, say, oh, this packet is for me, and it keeps it, and it passes it up through up to the next higher layers in its protocol stack. So now, at this point, and this is fundamentally how the internet works, basically. So every computer has and router has its own routing table that is indexed by packet address. You look up the address for a packet you receive, and the routing table tells you what interface to send out that packet if it doesn't happen to be for you, or what interface to use to send the packet on if the packet is not for you. But at this point, you're probably, or you should, have a bunch of questions about how this works. Namely, number one, how do we populate these routing tables with information? How is it that every router on the internet just happens to perfectly know what to do with every single packet? What about the size of these tables? So, a simplistic scheme would have one entry for every possible destination address. So one entry in the routing table for every possible destination address. That's fine when we're doing a 4-node example, right? The routing table would only have 4 entries. But what if we have 31 billion possible destinations? Is it possible to store a routing table with 31 billion entries? Well, it is, right? I mean, hard drives are certainly big enough for that. Addresses can be long enough for that. But it becomes impractical to keep these tables up to date. So if we have billions of entries in every single routing table, every time a node is added to the network, every time it's removed from a network, all of these routing tables have to change, and very quickly this becomes impractical. And so having one entry for every address isn't practical if we want to scale this up to the internet. And so, as it turns out, the solution is going to be using something called hierarchical addressing, which is going to be the topic of our next video.